So we have seen the total energy is the combination of pressure energy and kinetic energy. Kinetic energy is represented by the dynamic head and the pressure energy is represented by static head. So total energy is the sum of static head and dynamic head. Now the relative proportion of these two energies determines the degree of reaction. So if you remember the definition of degree of reaction, the parameter characterizing the proportions of changes in the dynamic and static head in the rotor of a fluid machine is known as degree of reaction, and it is defined as the ratio of energy transfer by the change in static head to the total energy transfer in the rotor. So if you see the definition, the static head is nothing but pressure change in pressure head, and the total head is nothing but sum of pressure head plus kinetic head, okay, or dynamic head plus static head. So in short, the degree of reaction is the ratio of static head to the total head, okay. So static head represents the change in pressure. So degree of reaction, it is change in static head upon change in total head. So R is equal to, if you see change in static head, it is also given by P1 minus P2 by rho g, okay, upon H. But P1 minus P2 by rho g, it is equal to 1 by 2g into U1 square minus U2 square plus VR2 square minus VR1 square. That's why it is also given by this formula. So this is the degree of reaction. So in short, degree of reaction represents how much is the energy transferred due to pressure change inside the reaction turbine. Okay. Now let us see what is the case for degree of reaction in case of impulse turbine and reaction turbine. Now for impulse turbine, we have seen that the pressure across the runner remains atmospheric. So there is no change in pressure across the runner in case of impulse turbine. That's why in case of impulse turbine, the degree of reaction is 0, because there is no change in pressure. So the machine for which change in static head in the rotor is 0 is known as impulse machine. As we have seen that the static head is caused by only change in pressure, and in impulse turbine the energy transfer in the rotor takes place only because of the dynamic head or the kinetic energy. So we have seen that pressure energy is completely converted to kinetic energy, and afterwards there is no pressure energy change in case of impulse turbine. That's why the degree of reaction is 0, as there is no change in static head. But in reaction turbine, the name itself suggests that why the name reaction turbine is given, because there is a degree of reaction for these turbines. So it is obviously it is not going to be 0, because there is a change in pressure across the runner. Okay, there is no atmospheric pressure across the runner. So that change in pressure across the runner causes the degree of reaction to occur. And for causing this change in pressure, the rotor is enclosed in a tight casing, airtight casing in case of reaction machines. Okay, so that there is a pressure change. In other words, casing has hydraulic function in reaction turbine. And remember, this degree of reaction ranges from 0 to 1, because static head, it is a part of total head only. So it will be obviously less than 1 only. Okay. In the maximum case, it will be 1, and in the minimum case, it will be 0. So the range of degree of reaction is from 0 to 1. So the impulse turbine example we know, it is a Pelton turbine, and reaction turbine, the example is Francis turbine and Kaplan turbine. So let us quickly summarize the important formula of reaction turbine, because we have to solve the numericals for reaction turbines. Okay, like impulse turbine, we have seen some formula. Here also we have to see the same formula for reaction turbine. If you remember the speed ratio, okay, there is no coefficient of velocity now. Okay, there is no jet in case of reaction turbine, because the water is directly striking to the guide vanes. Okay, so there is a speed ratio directly. Speed ratio, if you remember, the definition is same. It is the U1, that is the inlet runner velocity, divided by root of 2gh. That is called as a theoretical velocity, root 2gh. Okay, it's only general term given. So speed ratio definition will remain same. Okay, U1 by root 2gh at inlet condition. There is one more term added in case of reaction turbine, that is called as the flow ratio. So speed ratio, it is the runner velocity to the root 2gh. That is the ratio of runner velocity to root 2gh. While the flow ratio, it is the ratio of flow velocity Vf1 to the root 2gh, which is theoretical velocity of water. Okay, it is only the assumption. Okay, root 2gh, that is the velocity. Okay, corresponding. So flow ratio, it is Vf1 upon root 2gh. That you have to remember, these two definition. Discharge of the turbine, if you remember, in case of impulse turbine, it was given by pi by 4 d square into V1. Okay, V1 was the velocity of the jet, okay, coming out of the nozzle. So here the discharge of the turbine, now here there is no jet, so you can't take pi by 4 d square into V1. You have to take the area through which the flow is taking place. Now here there is no jet, so area will not be pi by 4 d square. Here instead of that, the water is striking to the guide vanes, okay, and the guide vanes are having certain width, okay, of that guide vanes, and there is a diameter, okay, at inlet diameter. So there is a circumferential area, that is 2 pi r1, which is nothing but pi d1. So pi d1, that is a circumference multiplied by this width, that will be the circumferential area. Pi d1 b1, that is the area. Instead of pi by 4 d square, it is now pi d1 b1 into Vf1. Now there is no V1, okay. In case of reaction turbine, the water enters radially into the runner, so that's why the guide vanes, when water is coming to the inlet of the runner, okay, runner vanes, so there is a area as a pi d1 b1 into Vf1, and by continuity equation it is equal to pi d2 b2 Vf2. So this is the formula for discharge that you have to remember. For Pelton turbine, it was pi by 4 d square into V1, while in case of reaction turbine, it is pi d1 b1 Vf1 or pi d2 b2 Vf2, where d1 is diameter of runner at inlet, b1 is width of runner at inlet, Vf1 is velocity of flow at inlet. This all terms you will come to know from the inlet velocity triangle. Similarly, d2 b2 Vf2 at outlet velocity. Sometimes the vane thickness, if it is considered, okay, along the circumference of that runner, then you have to subtract that vane's thickness, okay. If the thickness of the vane are taken into consideration, then the area will reduce because of that thickness, and that reduction in area will be pi d1 minus nt. N is nothing but number of vanes and t is nothing but thickness of each vane. So new area will be pi d1 minus nt, and that you have to take the modified discharge as pi d1 minus nt into b1 Vf1, okay, if the thickness of the vanes is given. Or sometimes it is given that the vane occupies this much area, 5% of area, so you have to reduce the that much 5% area from the total discharge. So total discharge, the modified discharge will be 95% of the original discharge. So that will be the case that we will see when we will see the numericals. Radial discharge. Now this is a very important term. In most of the numericals, sometimes you are given that the discharge is radial, sometimes it is given that vanes are radial. These are the two different terms, discharge radial and vanes are radial. What do you mean by discharge radial? Whenever there is a term radial discharge, then you remember there is a alpha or beta, that is absolute velocity angles, alpha or beta, they are 90 degree. So if an alpha and beta are 90 degree, then VW1 and VW2 are going to become 0. Okay, if you take alpha equal to 90 degree, then Vf1 and Vf1 and V1, they will coincide with each other. That's why VW1 will be 0. And if the vanes are radial, okay, that is not mentioned here, but remember, if the vanes are radial, then theta and phi are 90 degree. Okay, so if discharge is radial, then alpha and beta are 90 degree. If vanes are radial, then theta and phi are 90 degree. That means vanes are designed at 90 degree. Okay, so that you have to remember. But most of the cases, it is given as discharge is radial. So alpha or beta is equal to 90 degree. Whether discharge is radial at inlet or outlet, that will be mentioned in the numerical. Let us quickly see one or two numericals on the inward flow reaction turbine, radial flow reaction turbine. An inward flow reaction turbine has external and internal diameters as 1 meter and 0.5 meter respectively. Okay, so for inward flow reaction turbine, the external diameter means outer diameter is given 1 meter and inner diameter is 0.5 meter. So water is going to enter from outer to inner. That's why it is called the inward flow reaction turbine. So here your D1 will be 1 meter and D2 will be 0.5 meter. Okay, so that that notification that you have to remember. The velocity of flow through the runner is constant, means Vf1 and Vf2 both are constant, that is equal to 1.5 meter per second. Determine discharge through the runner and width of the turbine at outlet if the if the width of the turbine at inlet is 200 millimeter. So B1 is given as 0.2 meter. So you have to calculate B2, and discharge Q you have to calculate through it. You know the formula for Q is pi D1 B1 VF1 or pi D2 B2 VF2. So either of that you can use that formula. Once you know the discharge, okay, you can easily calculate the B2, okay, width of the turbine. So here external diameter is D1, internal diameter is D2, velocity of flow VF1 is equal to VF2 is equal to 1.5 meter per second, width of the turbine at inlet B1 is equal to 0.2 meter, B2 that you have to find. Q, the formula we know, it is pi D1 B1 into VF1, because you know pi D1 is the inlet diameter, that is nothing but outer diameter in this case of inward reaction turbine. Pi into 1 into 0.2 into 1.5, this will give 0.9425 meter cube per second, and you know pi D1 B1 VF1 is equal to pi D2 B2 VF2. So pi will get cancelled. D1 and D1 B1 is equal to D2 B2, because VF1 is equal to VF2, and once you put D1 B1 and value of D2 given, you can calculate value of B2. B2 is coming as 0.4 meter or 400 mm. Let us see one more numerical. An inward reaction turbine works at 450 rpm. Rpm is given under a head of 120 meters. Its diameter at inlet is 120 centimeter and the flow area is 0.4 meter square. The angles made by absolute and relative velocities at inlet are 20 degree and 60 degree respectively, with the tangential velocity. Determine the volume flow rate, power developed and hydraulic efficiency. Assume whirl at outlet to be 0. Whirl at outlet to be 0 means VW2 is equal to 0. That is the meaning. Okay, at outlet means VW2 is equal to 0. Here, first of all, you have to write the given data. RPM is given 450 RPM. Capital H, that is the head of the turbine. Okay, so reaction turbines are medium head turbines. Okay, the head is less, 120 meter. Diameter at inlet, capital D1 is equal to 120 centimeter or 1.2 meter. So flow area we know it is the circumferential area, pi D1 into B1, that is the 0.4 into 0.4 meter square. So that is flow area directly given as 0.4 meter square. So angle made by absolute velocity at inlet and relative velocity at inlet means alpha and theta are given as 20 degree and 60 degree respectively. Whirl at outlet VW2 is equal to 0. So the tangential velocity of the turbine you can easily calculate U1, because it is given as D1. D1 is given. So pi D1 n by 60 will give you U1 as 28.27 meter per second. Once you know U1, okay, immediately you draw the velocity triangle. It is very important to draw the velocity triangle for each numerical. Okay, so here V1 at angle alpha, VR1 at angle theta, in between V1 and VR1 there is U1, V1 and VF1 there is VW1, and here VF2 and V2 will coincide because VW2 is 0. That's why there is only phi angle, beta is 90 degree. So here beta is 90 degree as the whirl is 0 at outlet. So this is VR2 making angle phi. So in between VR2 and V2 there is U2, okay, and V2 and VF2 they will coincide. So this is the outlet velocity triangle. So if you consider inlet velocity triangle, tan of alpha is equal to VF1 upon VW1. So this will give you, because alpha is given, so VF1 you can calculate indirectly the relation between VF1 and VW1. So VF1 is coming as 0.364 VW1. So and U1 is also from inlet velocity triangle. U1 is equal to, if you see this VF1 upon tan of alpha, U1 is nothing but VF1 upon tan of alpha, okay, tan of alpha. So that is nothing but your, actually it is VW1, okay. So VW1 and U1, so you can calculate, okay, from these two relations. VF1 is equal to this and VW1 is equal to this. So U1 you can calculate as 14.17 and VW1, okay, that relation you can calculate as 14.178. So you can calculate the RPM. N is equal to 60 into U1 upon pi D1. So you can calculate the RPM as 225.65 RPM. Vane angle at outlet, U2 is equal to pi D2 N by 60. So you know pi into D2 is 0.6, okay. So that is you have calculated 60 into 14.178 upon pi into 1.2, that is inlet. So this is RPM. So once you know RPM, you can calculate U2, and similarly phi. Okay, and efficiency. Next we will see afterwards.